What we saw with the rat class was that when we want some features that the language doesn't provide, C++ gives us mechanism for creating that feature. So for example, with the rat class, we wanted a rational number class, way of representing rational numbers, fractions, and the ability to work with them and to integrate them into the general arithmetic classes, and it didn't provide it for us, so we created it with the rat class. We're going to do the same thing now with another example, and actually this example is, I think you'll find more interesting because it uses more of the features of C++, and it lets us dive deeper into how this actually works. So the one we're going to look at, we're going to call it a Safearray, and what we want to do is we want to address the following issue. Let's say, for example, in C++, you have an array like this, right? You say, I have an array A, it's an integer array, and its size is, let's say, 3. Right, so you can you can actually write something. I want to put something in A sub 2. I want to put a 15. But what would happen, for example, if I want to say something like this? I have an integer n, and I want to read the value of n at runtime, and then I want to say I have an integer array A whose size is n. Now, till the latest version of C++, you actually couldn't do something like this, and even now, it's not implemented in many of the compilers. In other words, I would like to be at runtime to determine what size my array is going to be, right? Until recently, you had to have the array of a specific size. The compiler had to know at compile time how big the array is going to be. What I'd like to do is at runtime, I'd like to provide some value and have the array be of that value. Until, as I said, till recently, and not always available in many compilers, that can't be done. Why that is has to do with considerations of efficiency. The compiler wants to generate the code as efficiently as possible, it needs to know where to put everything, and it wants to minimize the amount of work it has to do on the heap. This way, if it knows exactly how big the array is supposed to be, it could generate code efficiently and have the layout of all the variables in a way that maximizes the efficiency and minimizes runtime. So that's the first thing. We want to be able to have an array whose size can be determined at runtime. Second of all, imagine that I have an application where I'm, let's say I'm calculating my taxes, right? So I want to have a tax array with tax rates, but I want to say the tax array goes from, let's say, 2018, and I say I want it to go to, let's say, 2020, right? I can't do that, right? In other words, I can't independently determine the size of, the boundaries of the array. In C++, the array has to go from 0. If I say I have an array of size 10, the indices go from 0 up to 9. Right, but I'd like to do something like this because I want to say, take the tax rate would be tax, sub 2018, and it makes my code more readable. I can't do this, right? So if I'm building something, I might as well build it. So the first thing I want to do is be able to have the size determined at runtime, and the second thing, if I'm doing already, I might as well be able to determine the bounds of the array so I can write things that are closer to what I want. Third thing I want to be able to do, it's a wish list, right? And it's not provided by the regular arrays. Maybe we can build something that does this. If I have two arrays, one is A, is my array, and the other array is B. Can I assign an array A to array B? I can't do this. It's not possible. It doesn't let me do it. We'll see the technical reason. We'll see how this is enforced later on. But I'd like to do this, and I can't, right? So I want to build something, an array-like object, that's going to let me do that also. And finally, I want to be able to have my arrays being bounds checked. That's why I'm going to call them safe arrays, because if I would say something, as we saw before, I have an integer array, A is of size 3. What happens if I say C out A sub 3? Well, you know that there is no A sub 3 because it goes from 0 to 2. Right, that's where the indices are allowed. What happens if I do this? Usually, bad things. Right? Especially, I'm going to write into that. If I were to say A sub 3 gets 20, I'm going to be writing in an area outside of the array. Now, exactly what happens depends on the specifics of the application. It could overwrite some other information where other variables have been stored. It can do all kinds of things, and the specific remedy of this is not specified. Right? This is illegal, but and it's undefined. So what I like to do is I'd like to build my array, so my array is going to be safe. In other words, I want, if I do something like this, I want at runtime the checks on the bounds to be available, so that if I write a sub 3, I should have an error message printed and the program should terminate. Right? That's not what's happening now. It doesn't even happen with a vector. Right? If I have a vector of integers and I say that the vector is size 3, it also does not check for the bounds. And so I'd like to, if I'm building it, I want to be able to build it so it does what I want. And like we did with the rats, I might as well be able to print it. Right? So right now, I cannot say cout A. Some languages you can. Like there's a list in a list data type in Python. I could say print the whole list, right, by simply saying print A. Why not over here? Right? But I can't. I have to print it. If I want to print all the elements of A, I have to print them one by one. So just to reiterate, before we go into the details, these are the things I want to be able to do. I want to build a safe array that I can determine the size at runtime, like this, that I can determine the upper and lower bounds independently, which I cannot do with a regular array in C. I want to be able to assign one array to the other. I want it to be safe, right? That's why we're calling it a safe array. So there's bounds checked, and if I end up coming at the array with an index that's out of bounds, either less than the lower bound or greater than the upper bound, I want it to print an error message and terminate. And then finally, as we saw with rats, I want to be able to print the whole array at one time just by using the name of the array. Here's an example of a main program that might use some of the features. I declare a variable n, as we saw before. I input n at runtime, and I can declare an array of size n. Now notice we only have one argument over here, as we do over here. So what I'd like to happen over here, if there's only one argument, then it should be like a regular array in C++. It should start at 0. So if I say A10, it's going to go from A0 and to up to A9, right? Unless I specify the bound separately, it'll be like a regular array here. It's going to go, from 0 to n minus 1. And this is the one we saw before. And what about something like this? Well, we'll decide, right? I just say D is a safe array. We can decide. We're designing this thing. We might say it has 10 elements. It has no elements. We have to decide, right? So that's the first thing I want. And we already saw from the case of the rat class that these are going to be what? These are going to be constructor calls. Right? Now, what else do I want to do? So, for example, if A is a safe array, I'm declaring A to be a safe array, I want to be able to A sub I. In other words, I want to treat my safe array object. Now, this thing doesn't exist. We're going to build it, right? So, for example, rats, I couldn't say if R is a rat or X is a rat, I couldn't say X sub I, right? But with my safe array object, which is not an array, it's a new object we're building, I want to be able to use the index, and I want it to be able to act as if it were a real array, just like we have a vector. Right? If I say vector int, as we saw when we looked at vectors, I can also comment a vector with a bracket and it behaves like an array. Likewise over here, I want my arrays to behave like an array. So my array here is A. A goes from 0 to 9. So I want to be able to assign to it. I want to be able to print a whole array at once, however we decide to do it. I want to be able to assign one array to another. This is the array D. And this is the array A. I want array D to have the same value as A, and then I want to print it out just to make sure it worked. Right? I want to be able to print out using the bracket operation. I want to be able to sort an array. All these kind of neat things. Right? So how do we do? Let's go build one of these things and see how we support this whole wish list. As we saw when we dealt with rat class, when we define a new data type, a new class, there are two things we need to tell the compiler. Number one, what does it look like when I make a safe array? So what are you supposed to do internally? And then I have to define for the compiler the various things that it can do, right? And those we call member functions. So basically, we're going to have structure that looks like, so I'm going to say I have a new class, right? And the class is going to be called a Safearray. And I open it with this guy and I close it down on the bottom, right? And then there were two parts to this thing, right? The first part was, what does it look like? What's it made of? What's it made of? And then the second part was, what can it do? What can it do? And over here, this thing was private, and this guy here was public, right? We did this with the rat class. Let's do this now here, right? So basically, it's a new data type. We have to tell the compiler what the layout is going to be, and then we say what it can do. So let's see what it's going to be, but what do we need if you want to create one of these things? So clearly, if I'm going to say something like, look, I have a Safearray, all our Safearrays are going to be made of integers. And we can see maybe later on how we could generalize it. So I'm going to say I have a Safearray, and then my Safearray is, let's call it A. And in my Safearray, I want to be able to go, from, let's say, 5 to 10, right? So that means I have to have, when I build one of these things, I have to have a place for the 5, and I have to have a place for the 10. Now, this is going to be the lower bound on my array, right? The 5 is a lower bound, and this thing here is going to be the upper bound, right? The high, right? So I need at least places for the low and for the high. So somehow I'll put a 5 over here, a 10 over here. I guess since these are going to be integers, so this is going to be the low bound is going to be an integer, and the upper bound will also be an integer. So if I say it goes from 3 to 5, that's what it's going to look like. But now there's something missing over here, obviously, right? Because where's the array going to be? I mean, if I of course I have to have the lower bound and the upper bound, but I could have it at runtime determined as well. So if it goes from 5 to 10, how big is that? 5, 6, 7, 8, 9, 10, right? That's 6 places. So somehow I could put 6 places over here. But if I say it goes from 0 to n, and I don't know what the n is going to be, so where do I put it? How do I get this thing? So clearly, I would need a place for the array itself. So we're going to have a lower bound and an upper bound, and I need some place for the array. So that is going to be a pointer, and the array itself is going to be where? The array will be in the heap. All right. So that's what it's going to look like. So how do I tell the compiler that? Just like this, right? I have a Safearray. The class is called Safearray, and the private part, right over here, the private part, it's going to consist of these 3 fields. One called low. I'm going to write L. It's going to be easier, so it doesn't take so much room. And then it's going to have a high, which is the upper bound in the array. And then P is going to be a pointer to an integer. What does that mean? It means in the heap, this is going to be an integer array. Right? There's an array of integers, and P is going to be a pointer to that array. Okay, so when I say that's, and I could right now, of course, I could close it just like this, and so this is the here's the definition of my class, and all I've done though is I've defined this part of it. Of course, I didn't say what it could do, but just with this, I have a Safearray, and my Safearray is called A. And then what the compiler will do, will stamp out an object that looks like this. There's going to be 3 fields, one for a low. How is that going to be? It's as big as whatever the integer is on your computer, on your compiler. An integer for up, and the pointer, place enough for a pointer for the pointer to the array. So when I do something like this, it's important to keep in mind, because it'll become a little bit more subtle later on. Where is this going to be stored? Right? Remember, we had this memory model over here, right? And we had a runtime stack. Here's the runtime stack. And we had the heap, right, or the free store. So when I say I have a Safearray A, where's that going to go? Well, that's going to go right over here on the runtime stack. This has the same logical status as if I say I have an integer A. Right? So my integer A is going to be over here. Integer A is going to be over here. I'm sorry, let's make this clear. I have an integer I, so my integer I is going to be on the runtime stack over here, and this says I have a Safearray A, so I looks like whatever an integer look like, and my Safearray here with the 3 fields, that's going to be over here. But so what about this? So basically what will happen is a Safearray is sort of a schizophrenic item. It lives in two places. Part of it, right, the head of it, right, it lives on the runtime stack, but the actual body, right, where the array itself is kept, that's going to be in the stack. Now that in the free store, right, in the heap. Now that's going to cause some problem later on, and we'll see. We'll go into the details here because once if I put this in some kind of scope, so just like I will disappear off the runtime stack when it hits the end of the scope, A will also disappear, right? It's a regular variable. They live in the runtime stack, and once I hit the closing brace of whatever scope they're defined in, they will disappear. Yeah, that's true, right? This part will disappear. But what about the poor guy here, the actual array? Well, he won't. So we have to have some mechanism in the language that's going to allow us to make sure that we don't mess things up. And that's going to be called a memory leak. We have to be very careful with that. Okay, so we've answered the first question, that when I declare a Safearray, the compiler knows how to make it. So now what we have to do is we have to say, what can it do? What do we want it to do? Well, clearly, we're going to need a bunch of constructors. Because if I say that my Safearray A goes from 3 to 5, then somehow it's got to go someplace, right? The 3 has to go someplace, the 5 has to go someplace, the constructor is going to do it. If I say I have a Safearray, as we saw, B, I have to construct it. What does B mean? What does an empty array look like? Well, it's up to us to decide, but I have to construct it, right? If I have a Safearray C, right, and I say Safearray C is of size 10, I have to construct that, right? So we have to, that's what the constructor is going to do. They are initializers, as we saw before. So let's go through these constructors. What do we mean? Let's do them one by one. What do we mean when we have this Safearray over here? I say, I have a Safearray A, just like that. I have a Safearray, and his name is A. It's an empty one. What do I want to do? So, if we think about it, I might want to be able to say, what's the size of my Safearray, right? Or I might want to say, does it have nothing in it? Is it empty? Is my Safearray empty? So one possible way to have done this is to include in the definition of the Safearray, the declaration of what does it look like to the compiler, we could have had a size field, right? Could have had a size field. And if the size field is 0, we know that there's nothing in the array. That would have been okay, but it would have taken an extra integer. And sometimes we really like to make things as as simple as possible and as compact as possible. So there's another way to do this. Let's say I have a regular array A, regular C++ array. So I say my integer array A is of size 3. Now we know what this looks like, right? Here's the array of size 3. Its name is A. This is A sub 0, this is A sub 1, and this is A sub 2. Now how do I determine the size? Well, I have these two pointers, right? I have these two indices. It's going to go from 0 to 2. So I can take the upper bound and I can take the lower bound. If I subtract, I take the upper bound minus the lower bound. 0 minus 2, that gives me 2. But I have to add 1 because if I say 0 to 2, it tells me how many elements are between them. But I want to know the size, so I have to add 1. So generally, if I need to know the size, if I'm pointing at 2 elements in the array, so I take the upper, I take minus the lower, and then I add 1. Right? So that gives me the size, it gives me the number of elements between any 2 points in the array. I could use that same insight to do this for a Safearray as well. If I have the upper bound and the lower bound, what happens if my upper bound is minus 1? Right? Let's say my upper bound is equal to minus 1. Let's say my lower bound, and I'm over here, right? My upper bound, the high, is minus 1, and the low is 0. So we saw the rule is upper, which is minus 1, minus the lower is 0, right? This is the upper and this is the lower, plus 1. So how much is minus 1 minus 0? It's minus 1 plus a 1 gives me a 0. So if I set it so that my upper bound, this is my lower bound is 0, and my upper bound is minus 1, I can always take upper minus lower plus 1 to determine the size of the array. So what we'd like to do here is, we could have many definitions. I could say, for example, I could decide that if you don't tell me how big the array is going to be, it'll always be of size 10. That could have been, because we're the boss here, right? We decide what it's going to look like, but this is a reasonable thing to do. If there's nothing in the array, we can start it off with nothing in it, and so that what's going to be in the pointer field, well, there won't be anything in the pointer field, right? If we'd like, though, we want to have something in the pointer field. We're going to put a 0 here because we want to be very careful not to dereference some arbitrary bit pattern. So we can either put a 0 or put something else. So let's see how this thing works, right? That's what we want, and it's pretty simple how this works. Here is the definition of what happens when you have a safe array that's declared to be the default constructor for the safe array. So just as we saw, low and high and p are the three data members. So I set low to 0, I set high to -1, and then p is equal to null. Null is a constant defined by C++, and what it does is it puts a 0 into the field, right? And now null pointer is how you say in the modern C++. Right? Instead of null, there's a special constant called null pointer. But null would work as well, and 0 would work as well. Okay, so that is the default constructor. What about the 2-parameter constructor? So what do we need to do? Just let's think about it. So if I say goes from 10 to 20, so what I need to do is I need to set up my constructor now, right? I need to set up these three fields. This is low, this is high, and this is the pointer p. So if it goes to 10 to 20, I've got to put a 10 in the low, I've got to put a 20 over here, and I have to put some pointer in here, but a pointer to what? So I need to know the size of it. So the size is upper minus lower plus 1, right? Upper minus lower plus 1. So what I need to do is I need to go off to the heap, and to create an array of that size, I'm going to do that using new, and then it's going to return a pointer to me, and I'm going to put that pointer in here, right? That's what needs to be done, right? Again, this constructing means to initialize it. I want to set it up so I can actually use it. So in order to use it, I need to set the lower bound, the upper bound. I need to construct the array in the heap, and then a pointer will point to the value. So it's very simple. Once you know what you want to do, you can do it. Now, so what about the single parameter constructor? How is that going to work? So I say that I want an array x of size 3. So what's going to happen here, we decide that it's going to like a regular C array. The array, of course, is going to be in the heap. So I'm going to have the lower and the upper and my pointer p. The low is going to be 0. If I want an array of size 3, there's going to be 2, right? High is I minus 1. I'm going to go off to the heap. I'm going to create an array of size 3, and new will return a pointer to me, and that pointer will go in p. So that's exactly what needs to be done, and that's exactly what gets done. Okay, so we have all the constructors. But what do we want to do over here, right? We want to do assignment. I want to have, if I have a safe array A and a safe array B, I want to say A is equal to B. Now, in the rat class, we saw that we didn't have to define the assignment operator because we said there are 4 things that you get without using the new move operators, and one of them was an assignment. So we saw the assignment was there, and we didn't have to define it. Why can't we use the default assignment that's provided by C++? So let's remind ourselves what happened with the rat class, right? So if I have a rat x and a rat y, right? Here's x and here's y. X was 1/2 and y was 2/3. So if I say x is equal to y, the obvious thing happens, right? The 2 gets transferred over here. So this is 2. I don't change the 2 over here. And the 3 gets over here, and I have now 2/3. And so x is equal to y. These were built-ins, right? The integer built-ins, and it did exactly the right thing. So why can't I do that for my Safearray class? Why can't I just rely? I have 3 built-ins also, right? I have a low and a high. Those are integers. A pointer is also a built-in. Why don't I just copy them over? What's the problem? Why do I need to define an assignment operator? The answer is simple, because if we don't do that, if we don't tell C++ what we mean when we want to assign rats, the result will be disastrous. Let's see an example. Let's say I have my array A. Here is my array A over here. And so let's say the array A goes, just make it a bit smaller so we have enough room for everything. So here is my array A. And let's say it goes from 3 to 5. And there's going to be a pointer into the heap. 3, 4, 5. All right, so this is going to be 3, 4, 5. And so this is my lower, and this is my upper, and this is my P. And here is B. And so what is B going to look like? Let's say B goes from 2 to 3. So there are 2 elements in the array. This is low, this is high, this is P. And this is also pointing to something in the heap. And what it looks like, let's say it looks like this. All right, there's 2 elements. And whatever elements are in there. So let's say, so this is A and that's B. Let's say I say A is equal to B. Let's see what's going to happen over here. So if we just do the same thing to do with rats, in other words, I have an integer over here, right? An integer here, and a pointer over here. And correspondingly, right, these are both rats, these are both safe arrays. So these safe arrays have the same structure. Right, there's a low and a high and a pointer, and a low and a high and a pointer. They're the same types in the same places. So if I did what we did by integers, watch what would happen. So when I say equals b, I want this, in fact, to be 2. Right? I want the low over here to be 2 because I want it to be equal to b. So that's not a problem. I'm going to put a 2 over here. I want I want the 5 to become a 3. That's okay also. But if I copy the pointer from here to here, watch what's going to happen. So both this P and that P will be pointing to the same place, right? And that is a problem. Why is it a problem? Well, it's a problem for a number of reasons. First of all, P over here, the P belonging to A, was pointing to this guy, right? When I copy the pointer from B into A, it breaks this up. There's no more pointer to B, and to A's array in the heap, and what happens is this is lost. This is a very terrible situation. We saw what this was. This is called a memory leak. It's no good. Now here it's only 3 elements, so imagine this array is a gigantic array of 1,000,000 elements. So basically we've taken this 1,000,000 elements and it's completely lost to the program. The operating system the runtime system can't access it, and our program will probably crash because of lack of memory. That's problem number 1. What else is a problem? So another problem is that there is a principle when you write. So first of all, problem 1 is memory leak, right? Memory leak. There's another problem. The other problem is that there is a principle in software development, and it goes like this. We saw it before. It's called the principle of least surprise, and a specific corollary of it is do what the ints do. In other words, don't surprise anybody, right? And so if I have, let's say I have an integer I, let's say I is equal to 10, and another integer j, and j is equal to 20. So what does that look like in the memory? Right, here's I, and I has a 10, and here is j, and j has a 20. What happens when I say I is equal to j? So what it's going to do is it's going to copy, right? I is equal to j. So that's not really equal. What it means is take j and make a copy of j and put it in I, right? So this 20 is now going to be copied in here. But then what? Then as the program goes along, I and j, they're not connected at the hip, right? They're not Siamese twins that are connected at the hip. They go their merry way. This guy goes like this, and that guy goes like this. If I change j later in the program, if I make that 40, I is not going to become 40. I is going to stay at 20. Right? So what the ints do, in other words, what you expect in a C++ program in terms of the arrays, that if I say A is equal to B, just like when I saw I equals J, if I change 1, right, if I change something in A, I don't expect it to change in B. Likewise, if I change something in B, I don't expect it to change in A. But that's not what's going to happen. Since they're pointing to the same place, right, there's only one representation of the actual array. If I put a 5 in here, both A will have a 5 and B will have a 5, and they change in tandem, and that is not what I want, right? They get locked together, right? They got locked together, and that is not it, right? Locked together, right? That's the second problem. There's another problem as well. The third problem has to do with scope. What do we mean by scope? So just imagine the following. I have, I open up some scope here, and I close the scope over here, and I define some integer variable, let's say I, right? So what's the lifetime of I? There's no news over here. I pops into existence when it's encountered in this scope. And as soon as it comes to the bottom, as soon as I leave the scope, I gets the runtime stack releases I, and I is no longer in existence, right? It gets cleaned up. We call these automatic variables. Anything on the runtime stack behaves like that. So that's not only the integers or floats or chars or anything. It's any kind of variable, anything that's a variable, including Safearray variables as well, because we want to do as the ints do. So watch what's going to happen. Remember, we want to clean up when we leave the scope. So let's say I say the following thing. Outside, I have some Safearray B, right? And let's say B goes from 2 to 3, right? So that's this guy over here. And inside, I have a Safearray A, and I say A is equal to B, the situation that we have over here. So if we do what we saw was going to happen, so what will happen is that A is no longer, if we copy over element by element, so it's no longer going to be the case that each one points to their own array in the heap, but this 2 will go over here, and this 3 will go over here, and this pointer P will come over here, and this will no longer point to that, right? But rather it's going to point to this. We saw that was problem number 1. But now look what's going to happen. A is defined in this scope. We said A is equal to B. We want everything to behave like the integers, automatic variables, which means all automatic variables declared in a scope. When I exit the scope, I want to get rid of them. I want to clean them up. Well, since A is defined in the scope, I want to clean A up. But what do we mean? What does it mean to clean up A? What does A look like? We saw before that this is a very complicated situation. Here I have the runtime stack. So A, which part of A, right? The lower, the upper, and the pointer live on the runtime stack, but the actual array lives in the heap. What I want to clean up, of course, is both pieces. I don't want to leave this in here. I have to clean this up, and I have to clean this up, right? I want everything that was A to disappear once it exits the scope. Now, we didn't see how to do this yet. We'll see that in a little while, but we certainly want that to happen. So what's going to happen is not only will the part of A that's this part, right, sometimes called the handle, not only the handle, but what's controlling, right, it's also going to go away. But since we said A equals B, it's not this. It's now pointing over here. So when it cleans up, it's not going to clean up A's old array. It's going to clean up B's old array. This is going to disappear. When I come out of the scope, B rightfully thinks, well, he's okay. Everything that he had before, he has, but that's not true. Because when we cleaned up A, since the pointer in P was pointing to whatever, the point A's pointer is a copy of B's pointer, so the compiler had to arrange the code to give this back as well, right? Not this part, but to give the point it's pointing to. And so B is going to be very surprised when this over here, right, is no longer available. Right? So the problem of wanting to clean up the scope, we're going to end up that B will no longer have whatever he had before. That is bad, right? So we have the memory leak problem. That was problem number 1. We have the lock together. When I change A, I change B, and that's not what we want, right? Some languages actually do that, but C++ doesn't. Right? I say I is equal to J. Changing one does not change the other. And we saw that the cleanup after the scope is going to end up that if I have a situation like this, where I have one variable defined outside the scope and inside the scope, and if I assign A to B, cleaning up A destroys what B points to. So therefore, if we cannot rely on the built-in assignment operator, which would just copy the values in there, right? Such a copy is called a shallow copy. Shallow copy. Right? Because it's not copying deep into the structure, it's just copying the structure itself. So how do we fix it up? Well, if you think for a moment, the answer has to be obvious. Well, we can't do this. What we really want to do, when I say A is equal to B, I want A to have a copy of B. I don't want A's pointer to point to B. I want to B's pointer, right, to the elements in the runtime stack. What I want is that the pointer A, P's pointer, the pointer of P in A should point to a copy of what B points to, right? And it'll be completely independent, and then I'll solve the problem, because changing the array A will not change the array B, and I'll be doing what the ints do. But I have to, of course, take care that I return it. They're not going to be locked together, and I won't have a problem with the scope. So let's work out the details, but that is the big picture. First, a reminder. If I have a member function f, right, member function f of some class, the basic syntax, the real syntax, before I use the syntactic sugar, there's an object of the class over here. Let's say it's called x, and then I say a dot, and then I have the member function, and then whatever parameters the member function has, right? And I can use the variables of x directly. That's the way it works. And if I have an x object coming over here, you have to access the x object. Like, remember the numerator and denominator when this was let's say the operator plus over here. So here I said numerator and I said denominator, and if the variable here, remember from the rat class, if it was r on the right hand side, so it was r.n and that r.d. We access the member data members via the argument, by the parameter over here. So the same thing over here. So when we say operator plus, if I say A is equal to B, and these are rats, what really is happening, it's A, which is a rat. I'm sorry, these are Safearrays. A dot operator assign equal, and then B is going to come in as the argument. Right now, remember what we have over here. We have a high. What are the elements here? I have a high, a low, and a high, and a pointer P. That's what the arguments are. So if I want to talk about the low and high and P of A and B, here I'll talk about it directly. That's going to be low and high, and that's going to be P. But if it's going to come over here, and it's going to come through the parameter S, so when I want to talk about it for the argument I'm passing in, that was for B, so it's going to be S dot low, S dot high, and S dot P, right? That makes sense. It's exactly what we did when we were talking about the rat class. Okay, so now that once we got that out of we got that clear, let's just make sure again what we want to accomplish. What I want to do is I want to get the following to happen. I want to look at B. I want to look at B, and I want to see how big the array is, how big B's array is. Why do I want to do that? Because I want to recreate it for A, because I want A to have a copy of B's. I don't want A to point to B's array. I want A to have a copy. So, well, I know how to do that. I go to low and high for B. That's going to be what? Where's the low and high of B? It's high minus low, but I have to access it through the parameter. So it's going to be S dot high minus S dot low plus 1. That's going to tell me how big this thing is. I'm going to go off to the heap manager and say, give me that many, right? I'm going to, but before I do that, I have to make sure that I give this back, right? Remember, we saw how to do this. We saw that if we take something in the heap with a new, we have to use delete to get it back, right? So we're going to do that over here. We're going to have a delete. We're going to delete the value of A and P. What's that for? Because we don't want to have a memory leak, right? Memory leak. We don't want to have the memory leak. So since A is going to be a copy of B, I just want to give this thing back. And we're going to go through all the steps in detail, but just remember what we have to do over here. So we're going to have to delete what P is pointing to. I'm going to go over here, see how big it is. I'm going to ask the heap manager to give it to me. I'm going to copy the values in here. So this is going to say 50 and 60. This is going to be pointing down here. Have to change this and this, and pretty much I am okay, except for one glitch. Okay, so let's actually do this. So this in green we will see later on, and likewise this, right? And likewise this. but everything else is what we talked about. So let's go through step by step. The first thing we want to do is we want to delete P. Now, what does it mean, P? The left-hand side, A has a P and B has a P, but we saw this already. This is low, this is high, this is P, but this, since it's coming in through S, so this is going to be S dot low, S dot high, and S dot P. So when I say delete P, right, delete, why bracket? Why bracket? Because it's an array that I'm pointing to. What that's going to do is it's going to take this and return this to the heap manager. So we're not going to leak this memory, right? That's step number one. Check. This is excellent, right? Excellent. We make sure we don't have a memory leak. What do we want to do now? Now we want to go over here and we want to see how big this is, and we want to get enough memory so we can actually make a copy of this over here. Well, how big is it going to be? So it's going to be S dot high minus S dot low plus 1. So that's what we do here. We say, I want S dot high minus S dot low plus 1. That's going to be the size of the array, the new array for A. And now I go out to the heap manager and I say exactly that. I say I want an array of integers. Give me an array of integers of the appropriate size, right? In other words, what we just did up here, in this case, is going to be 2. It's going to return a pointer, and I'm going to put that pointer in P. What is P? P is A's P, right? So P is going to point over here, and it's going to copy how many elements I had here. I had 2 elements over here, 2 elements over here. Now what do I have to do? I have to copy every element over here. I have to copy it over here. Well, I use a for loop. Now remember, a pointer to an array is the same as the name of the array. So what is this array called? Well, P, here's P. P is pointing to this array, so the name of this array is P. What's the name of this array? What's the name of this array? Well, what is pointing to that array? S dot P, right? S dot P. So the name of this array is S dot P. The name of this array is just P. So I'm going to simply say P sub I gets S dot P sub I. In other words, copy everything here into here. And how many? So I starts at 0, less than size. I do that. So at this point, I'm going to get a 50 over here and a 60 over there. And finally, what I need to do, I need to copy this and this into this and this. So this is, again, modified by the parameter S. So I say low gets S dot low. So the 2 is going to get copied into here. High is equal to S dot high. So the 4 is going to be equal to here. And I've completely made the A into a copy of B. And that's cool. I finished. Except for one other thing. I have to explain what what this thing over here in green is, and I have to explain the return type and why we're returning anything at all, right? If I say A is equal to B, or let's put the integers, right? When I say I is equal to J, so I don't return anything, do I? I is equal to J. So why over here do I need to return anything at all? So that's a good question, and we'll deal with that now, and then we'll explain both this here and the return type. So first, let's deal with the question with integers. If I say I is equal to J, well, do I return anything? Or does it just, put J and I and that's it? So the answer is it does return something. And what it returns is I. It returns the name of the variable on the left. This is part of a general notion of what C++ does when it does evaluations of things. So if you have something to evaluate, for example, this is an expression, and C++ evaluates expressions. So what happens when you evaluate an expression? So the evaluation expression produces 2 things. First of all, it produces a value. And then it produces something called a side effect. So let's start with a side effect. Right? A side effect is the change in the system that happens because of the evaluation. So let's say I is equal to 3 and J is equal to 5. When I say I is equal to J, this 3 gets erased and I get a 5 in its place, right? So the side effect is the change, in this case, in the RAM that happens because of the expression I is equal to J. That's the side effect, right? What do we mean by the value? The value is what it says. The value is the value. So here's an example of the value. Let's say I say cout and I equals 5. So I equals 5 and j equals 6, right? So I say I equals 5, and so when I do that assignment, I is now 6. What do we mean by the value? So let's say I say cout before I do the assignment. I just say I is equal to 5, right? Let's say I. So I say cout I. So I'm going to get a 5, right? Because that's what's in I. But really, it's a two-step process. It doesn't print the letter I, right? It goes and evaluates. This is an expression itself. It evaluates the expression I, and the value of I happens to be 5 initially, right? 5. Now, what happens if I say cout I is equal to j? I gets assigned to j. So first of all, it doesn't print I equals j. So this is an example of an expression that's evaluated. And what happens is, this is going to put the j into the I. So I is now going to change from 5 to a 6. But then what? What's it going to print? So it returns the name of the variable on the left-hand side. So the first thing that it did was the assignment created a side effect that the bit pattern in I changed to be equal to the bit pattern in j. And then the value of this was I. So now it's as if it says cout I. So it looks in I, it sees a 6, so it prints a 6. Right? So whenever you have assignment, it's important to know, whenever you have assignment, the value of the assignment is the name of the variable on the left-hand side. The side effect is the changing of the bit pattern or whatever it is from one bit pattern to the other one. Right? I originally had some bit pattern, now it's going to have the bit pattern of j, for example, with the integers. But what gets returned is the name of the variable on the left. So if the rule here is do as the ints do as the ints do, so when I say, in our case, when I say A is equal to B, then if I want to do for the safe arrays what I do for the integers, I have to return A. So how do I return A? So here's the return, and it says return star this. Now the question is, you have to remember what this is, right? Remember what this is. This is the address of the variable that we are working on. So just to review, when we said A is equal to B, we saw what this really means in C++. We have the thing on the left, the dot, and the operator, in case the operator was operator equal, and we passed the B in here, and what was the object on the left? It was A. So this is the address of the guy on the left-hand side. In our case, this is the address of the safe array A. It's the address of the thing on the left-hand side. Now, the address is a pointer. What happens when I take a pointer, right? This is a pointer. What happens when I take a pointer and I dereference the pointer? What happens when I do that? I get another name for the thing that gets pointed to, right? We saw this way, way back in the early part of the semester. So that means star this is another name for A. Now, how do I say a name? A name is referring to something. And so star this is the name of a safe array. So that's why we say it's returning a safe array reference. A reference is another way of saying a name. So it's a safe array reference. That's why we say return this, because what we're going to do is the ints do. We return the thing on the left. Now, finally, what's this green thing over here? So let's say, I mean, people aren't going to do it necessarily, but you have to take care of all the possibilities. Let's say I say A is equal to A, right? I just assign A to itself. I can do that, right? So what does that mean here? What does that mean over here? So let's look at these data fields. So this is called L and H and P. But if I say A equals A, so this is also called, because the parameter here is S, this is also called S.L and S.H and S.P. So what's going to happen? Let's go through this. So first thing it's going to do is it's going to delete P. Remember, there's only one thing. It's A equals A. So it's going to delete P. It's going to take this over here. It's going to take the whole thing, and give it away. It's not going to be there anymore. This goes away. It's back in the heap. And now what happens? It's not there. So I say over here, I get s dot high, s dot low plus 1. That's still same numbers. I still get I get a 3 over here. I get that same 3. And now what I try to do, and I get an array, right? I get an array, size 3. That's what's happening over here. And P is pointing to that new array. P is pointing to that new array. But it's going to say P sub I is equal to S sub P sub I. But there's nothing in here. There's nothing in it. It's brand new piece. I'm not going to be copying this because I gave that away. Right? It's not there anymore. So this whole thing does not work. It's not going to work. It doesn't make any sense. So what I need to do is I need to be able to detect, am I in a situation where I'm saying A is equal to A? Now, how do I do that? Well, one way to do that is to check the address of the left-hand side, address of the right-hand side. Now, remember, when I use the assignment operator, so when I say A is equal to B, what do we say that was? It's really A dot operator equal and then B. But if I'm saying A is equal to A, then this is an A and this is an A. Both of them are A's. So if I take the address of this and I take the address of this, they'll be the same. That's how I know that the one on the left and the one is the parameter are the same. Well, what's the address of the one on the left? We saw that. The address of the one on the left is this, right? That's the address of this one. What's the address of this one? Well, the parameter is called S, right? So the address of it is the address of S. So if we have a situation where they're equal, if the address of the left-hand side is equal to the right-hand side, I know I have a situation of A is equal to A, and so I don't want to do anything, right? It's going to mess everything up. I simply want to return the name of the one on the left, which is A. Well, this is the address of A. Star this is another name for A. And that's what I do. I return star this as a Safearray reference. And finally, let's take a look at the parameter I'm passing into operator assign. And that is a Safearray reference. So I'm passing the Safearray when I say A is equal to B. I'm passing B in, but I'm passing it in by reference. That makes sense, right? Why copy it? The alternative for passing by reference is passing by value, which means I'd be copying B. Why should I do that? I only need to refer to the lower and upper and the P of S. Since I do that, S dot low, S dot high, S dot P. So I don't need to copy them in to the function. So I pass it by reference. And why by a const reference? We saw that last time because when I say A is equal to B, I want to make sure that I don't end up changing B, right? So by making it a constant, it's guaranteed. If whoever's implementing the function tries to muck around with by changing anything from the from S, the compiler won't let it. It won't compile. So this is a fairly standard thing, right? If I have assignment, I'm always going to be passing in by reference to the type. That's the basic idea here. Now the next thing we're going to look at is the copy constructor. So what's a copy constructor? So remember when we first started looking at this one, we looked at the end of the rat class. We said that C++ provides us with 4 + 2 functions for free. One of them was a default constructor. But we defined our own constructor for this class, for the Safearray class. The next thing you get is assignment. But we saw that if we use the default assignment, it's not going to work. So we defined our own assignment operator. The third thing that you get is something called a copy constructor. And that's what we're going to look at right now. So what is a copy constructor? Let's just see what the words imply. It's a constructor, which means that it's going to be initializing some variable of class type. In this case, since the class is a Safearray, it's going to be initializing a Safearray with a copy of a previously constructed Safearray, right? That's why it's called a copy constructor. It's for initialization. It's a constructor, but by using a copy of an existing Safearray. Now, where would that happen? So it says right over here where it's going to happen. It's going to happen when you pass by value. We're going to call the copy constructor to initialize, to construct the parameter in a function. So let's take a look what that means. Let's say, for example, I have some function, right? And the function takes an integer I, right? And let's say I call the function with f of j from the main program, and j is equal to 3, right? So that means I have a 3 over here. This is j. There's a 3 in here. Here is the function. In the function, I have a place for I. Remember, a variable is a local, a parameter is a local variable. So when I do a pass by value, what does it do? It copies the value over here, the j, into the value in the I, right? So what's going to happen is the bit pattern in here, in the j, this bit pattern over here in j, is going to get copied into I. I'm going to get a 3 in here. But remember, everything that happens in Vegas stays in Vegas. Anything that I change here in I is not going to affect the outside, but I'm going to get a copy of the bit pattern in j. So imagine I have a Safearray. So when I have a Safearray, let's just see what happens if it's not an integer, but f is a Safearray function, and it's, let's say the Safearray function is y, and I call f on some Safearray x. So I think if you think for a moment, you'll be able to see what happens. So y is a local variable. Here is y. It has the upper, and it has the lower, and it has the pointer p. And then here x is on the outside, right? Upper and lower, let's say 3 and 5 and a pointer, right? And if I do a pass by value, remember what it's going to do. It's going to copy the bits. So it's going to copy the bits of the lower into here. It's going to be a 3. Copy, right? So there's going to be a 3 over here. It's going to copy the bits from the 5 in here. And it's going to copy the bits of the pointer into here. And we have that same situation we had that required us to write the assignment operator. Because, right, here is the scope. What happens when this y, which is the parameter which is local to the function, what happens when the function ends? Well, y disappears. So remember we said what happens in a scope when something disappears, we clean it up. So we're going to end up cleaning up what? We're going to end up cleaning up not only the part that's on the runtime stack, but what it points to. And since it points to the same thing, since y points to what x is, because I just copied the bit pattern over here, it's going to destroy this. It's going to give this back when I come out, so x will have just lost its representation. And so it's a real problem. It's the same thing that happened that required us to write the assignment operation. It was the same thing that we saw, that we defined some Safearray B on the outside and some Safearray A on the inside, right? And we said A is equal to B. It's the same thing, right? Because it's a scope. X is on the outside scope. Y is on the inside scope. It's the same thing that we saw before, right? So we have to do essentially the same thing. This copy constructor basically has to do for the local variable in the function what we did in assignment. Namely, let's just articulate it. What did we do with assignment? We didn't want this crazy thing to happen over here. So what we did was we reconstructed in the local scope, right? In the local scope of the function before we just had a scope, we didn't have a function, but now we have to reconstruct the variable, what's x has, right? Whatever x has, we have to reconstruct it. So y is going to look like this, and it's going to be having a copy of the outside, and it'll be changing its copy, and that's the semantics of pass by value, right? When we pass by value, anything we change on the inside doesn't change on the outside. And since y has a copy of x, any modifications it does on, let's say, this array has no effect whatsoever on x, right? That's the idea. So now if you think about it, what's the difference between the assignment of A is equal to B or passing B as a parameter by reference? What's the difference? So the difference is very simple. The difference when I say A is equal to B, so A is pointing to something, right? And B is pointing to something. And the first thing I need to do is need to get rid of that. But when I, right, that's what I did when I made assignment. But when I pass it in to a function, so the local variable, in this case the variable y in the function, has no value. So I don't have to delete it. All I have to do is basically the guts of what I did for assignment, just this part over here. I have to reconstruct on the inside of the function the safe array that gets passed on the outside. So I figure out how big it is, I get its size, I create an array from the heap, I put it in P. Who is P? P is the local variable. It's the pointer of the local variable, and I copy over what's in S, right? Copy over what's in S. I set low and I set high, and notice what I'm not doing. There is no return. There is no return, and there's no return type. Why? Because this is a constructor. A constructor does not have a return, right? It's just an initializer. So that's why there's no return. That's why there's no check. Can't be a case of A equals A, because I'm taking a copy of A and putting it into a local variable. That can't happen. So there's no test that we had over here, right? Likewise, there's no return because it's a constructor. So this is a very important idea. And copy constructors, again, are used when you do initializations, when you're passing in objects of class type, when you pass them in by value, and actually 2 more times, right? So let's make that clear. So when is this copy constructor invoked? So the first time it's invoked, we just saw now. It's invoked when I'm passing objects of class type by value. That's the first time. When else? So the other time could be when I am returning by value. Why? What does that mean? Let's make sure we understand what's going on over here. So let's have a function, regular function f, that takes some parameters, and I return this thing by int, and I return an integer, right? So I do some calculations, and let's say I have some integer z, right? And then at the very end, after the calculations, I say return, right? I say return z. So and how am I returning z? I'm returning z as an integer. How does a function return a value? How does it return a value? So if you think about it, there's something of a paradox here. Something of a paradox. Why? What would be the paradox? Because if I have let's say z, right? Z is what? What is z over here? Z is a local variable, right? Local variable. What's the lifetime of this local variable? It's just to the end of the scope. If that's the case, then as soon as it hits the scope, when I say return z, it hits the scope. Z doesn't exist anymore. So what's it returning? Let's say I say in the main program, m is equal to some f of let's say I. F of I returns z. I got to get z over here, but as soon as I hit this, there ain't no more z. And it doesn't return before it hits, because what does it mean return? Go where? Go home? Where does it go? Right? So what really happens is hiding in the background, and there's a lot of technical things over here that I'm mentioning. Interested, you can take the advanced C++ class that we give later on in the sequence. But basically what happens is some other hidden variable, Q. You don't see it. It's just defined for you. And what will happen is that before the closing brace, the compiler arranges so the value in Z gets into Q, and Q is not in the same scope of Z. You can imagine Q is global to F. So when the function f finishes, q still is alive. So before the scope is closed and z still exists, the value in z, whatever the value is, goes into q, and what gets returned for f of j is the value stored in that hidden variable q. So, but think about what has to happen. Since I'm returning, in this case, I'm returning by value, there's an integer variable, and I'm returning that integer variable, or a float, or for that case, I could be returning a safe array. This could be a safe array to a safe array, right? But I'm returning by value. That means that this z is being used to initialize this q. Well, how? By value. So that's why when I return by value, I'm also calling the copy constructor, right? Because z, before it gets killed over here, right, while it's still alive, is used to initialize this variable q. Well, I'm initializing a class object. Imagine it's a safe array, for example. With a safe array, that is a copy constructor. I'm constructing with a copy of an object of the same type, right? So the second time that the copy constructor is used is when I am returning a class object by value. And the final time when it's used is initialization. So what does that mean? When initialization, so a case that would look like this. Let's say I have a safe array, x, right, and let's say it's 3/4, 3/5, I mean 3/5. And now I want to say, I have another safe array, and it's z, and I'm going to initialize z with x, right? So what's happening is I'm constructing, this is initialization, not assignment. So I'm constructing this safe array with a copy of this safe array. So I'm initializing, I'm constructing z with a copy of a safe array, a copy of an object in the same class. So that's the third time. So initialization, right? Initialization is another time, right? When I initialize a class variable with a class variable, that's the third time that copy construction is invoked, right? So that's the copy constructor. Now, things have changed significantly, and there's new ways to do this. Those are called move operators. And stay tuned for the next exciting episode, but not in this course. In order to finish up the description of our Safearray class, there are three more things we have to talk about. One is a destructor, which we have right over here. I'm going to talk about the bracket operator, so I could treat my Safearray as an array, and then finally take a look at input-output. So what's a destructor? What is that about? So we saw the issue, right? I have some kind of a scope, and I declare a Safearray, let's say A5 in the scope. So what happens over here? What does it look like? It looks like this: 0, 4, and this is on the runtime stack. Right, here's the runtime stack, and this over here is pointing all the way down over here where the actual array is, and this is in the heap. So when I close the scope, and so the scope is from here to here, so this is a local variable. So it's like saying integer I. So when I exit the scope, I goes away because that's on the runtime stack. Likewise, the safe array A goes away. But the safe array A, as we saw, lives in two places. Part of it, right, this part, that lives on the runtime stack. But the other part, this part here, lives in the heap. So how do we get the heap part to disappear as well? We want it to happen automatically. So that is where the destructor comes in. And here's the idea of a destructor. Now, just like you don't need, the language does not require you to define constructors, right? The constructors, they construct for you, right? They initialize. If you don't want to initialize, you want to do it yourself, let's say with the setters, go ahead. So likewise, you don't have to, but if you do define constructors, they will be called in the appropriate place, right? So if you say, I have a safe array, going from 3 to 5, so that's a constructor call, right? You don't have to do that, but if you write that, if you make constructor, constructor will be called. Likewise, you can call a destructor. And what the destructor will do is, again, you're not going to call it. You won't call the destructor, though it's legal to call it, whereas it's not legal to call the constructor. It is legal to call a destructor, but again, that's a more advanced topic. But what happens is, if you have a class object, in this case, our object A, and there is in your class a destructor defined, so when that object A goes out of scope, like in this case right over here, when it goes out of scope, before it goes out of scope, the destructor would be called as if, what's the name of the destructor? It's called, this is the name of the destructor. We'll do this in a second, the details. But as if right over here, the following code is inserted for you. Right before it goes out of scope, the code will be A, that's the name of the object, dot, and then the destructor is called tilde A. Now, why this? Because it's like the negation sign in logic, right? It's like negate, right? Not. It's like the not. So it's a sort of a, if the name of a safe array is the name of a constructor is the class name, the name of the destructor is the same as that a class name with a tilde. Okay, now notice there's other similarities. What's the return type of the destructor? No return type, because all the destructor does is it destructs, it undoes. We'll go into that in detail. And also notice that the destructor takes no arguments. You can't pass any arguments to the destructor. The implication of that is you can only have one destructor. Because remember, we talked about operator overloading. If I have a function f or function plus, whatever it is, the way that I distinguish different versions of that is by looking at the parameters, right? Looking at the arguments that are allowed to get passed into the parameters. But if I can't have any parameters, then there's no way of distinguishing, different versions of this, which means I can't have different versions. So you can only have, while we saw you can have multiple constructors by simply changing the parameter list, you can only have one destructor. Okay, so let's see what the destructor does, right? It has the effect of right before this variable A goes out of scope, calling the destructor. Remember, the destructor is a member function, so it has access to the member variables of member variables of the object, right? So what is this destructor doing? What is it going to do to A? What's it going to do to A? It's going to go to A, and what does A look like, right? This is, let's say, my A, the local A inside the function. So A has a lower, right? It has an upper and has a P, right? And P is where it's pointing in to the runtime stack, right? This is pointing in here. So what it does is it calls delete on P, right? Basically, before the whole thing goes out of scope, before this Safearray goes out of scope, A, so the destructor, which is being called on it, right, effectively saying something like to A, apply the destructor function. The destructor function says reach into A, go to the P variable, right, go to the pointer, follow to the pointer, and then give it back, right? Give this back. And so you're not going to leak the memory. And then what happens? And then when it hits the closing brace, so since this part, right, this part lives on the runtime stack, well, then just it's an automatic variable, right? It's an automatic variable, just like, let's say, I would be an automatic variable. So just as if I have a local variable I, as soon as the scope is closed, I goes away. So likewise, this part of the Safearray, right, the handle, so to speak, of my object also goes away. And that's how the cleanup happens. So while a constructor constructs, a destructor just finishes up. It's like a finalizer. It destroys and it takes care of all of the cleanup. That's what a destructor is. It's not like a Dementor in Harry Potter. It doesn't harm anything. It's actually quite useful, right? It cleans up for you. So that is a destructor. So you have, what do you have? You have a default constructor, which we saw for free, but we defined our own. You get for free an assignment operator, we defined our own. You get a copy constructor, we defined our own. And finally, you get a destructor, but we defined our own, right? Now you might be wondering, what in the world does it mean? You get you get it for free. How does it know what to do? What does it mean you get it for free? So the answer is something like this, right? Let's say I have a class that consists of pre-existing objects. Let's say, for example, I have a student class, right? Let's have a class called student. And what does my student consist of? Let's say it's a string called name, right? And it's a string called, let's say, ID. And let's say it's a float called grade, right? And a bunch of other stuff, right? So this is the private part, right? And that's what my object looks like. So now, if you think about it, string, it comes with the C++ library. So does string. And float, well, float doesn't need to be cleaned up, right? So my object, my student object, would look something like this. It would have a place for a name, right? Name would be here, but that's a string. And then ID would be here, but that's also a string. And then let's say grade would be here, but that's a float. So what happens if in a scope I have, some student, let's say A is the name of a student, right? I say student A, and I do that in this scope over here, right? I have a scope and I have student A in the scope. What happens when A goes out of scope? So, and I don't define a destructor for a student class. So what C++ does is it looks at the component objects in my class. This is how it synthesizes its own destructor. It looks at the objects in here, and if those objects have destructors, it'll set up this default destructor, the one it synthesizes for me, not the one I write, right? If I don't write it, it provides one for me, and it's going to call the string class's destructor on name. Right? So it looks at every component of my definition, and if I don't define a destructor, it'll give me one, and what it gives me is it goes through exactly those components of my object that have destructors for those classes, and it calls that on those sub-objects. Right? So that destructor is going to destroy the name string and the ID string, and nothing to destroy over here. It's not pointing to anything anywhere. So this will do the right thing. So that is the idea of a destructor. It's automatically called whenever the object goes out of scope. It doesn't make a difference where. So for example, if it goes out of scope by falling out of the bottom, right? When I didn't have to say return, it implicitly returns over here. But if any object in the class, if I define a destructor for the class, the destructor will get called and it'll return whatever is on the heap, right? Same if I return in the middle, no matter where I return from, the destructor will get called. So it's a cleanup function, and essentially what it's doing here is it's guaranteeing that you're not going to have a memory leak by forgetting to give back the elements that are on the heap, to give them back to the memory manager. Right now, we're ready to get to the main theme of the whole exercise. Why did we make the Safearray object in the first place? So when I say that I have a Safearray, the Safearray is an array. That means if I have this Safearray X, and I say that X goes from 10 to 20, I have to be able to say X some something where the something is between the 10 and the 20, right? So there are two issues here. First of all, I have to say if I say X sub 2, if I say X sub 12, let's say, it's supposed to get me an element someplace, and that element's going to be stored in the heap. That's the first thing. And second of all, so in other words, it has to behave like an array. And the second thing is it has to behave, that's the array part. And then the second part is it has to be safe. That means if I say, if I claim that my array X goes from 10 to 20, and I say X sub 120, I should get an error message, right? It shouldn't let me do that, right? So that's what we have to do now is we have to implement something that gives me that functionality, okay? So let's take a look at this. In order to do that, if I have this array x, I have to be able to say x sub something, right? Let's say x sub 12, right? So in order to do that, I have to make sure that C++ compiler understands the bracket operator when applied to my Safearray. Because in fact, the Safearray class, when you create a Safearray, the Safearray is not an array. As far as C++ is concerned, an array is an array. Now, I would have to say int I, int a, let's say 10, right? So it knows that it's an array. But a Safearray is not an array. It's an object, and we have to give it the functionality so that it behaves like an array. In order to do that, I have to overload operator bracket. Okay, that's number one. So how do we do that? So let's see what happens when I say I have a Safearray and it goes from x goes from 10 to 20. So we saw already what happens. I have an object x, and what does x look like? What does x look like? So x goes, it has a 10 over here and a 20 over here, and has a p, right? So this is lower, and this is an upper, and this is a pointer, and the p goes into the heap, and in the heap I have an array p, right? Now remember, a pointer to an array is the same as the name of the array, but p, the internal array, that is p sub 0, p sub 1, p sub 2, p sub 3, and so on. My user, this is x, right? My user is going to say x sub 10, x sub 11, x sub 12, up to x sub 20. So we have to have some way of matching when the user thinks he's using an array x, and his array looks like this. So his view of the array is that this is x sub 10, and this is x sub 20, and this is, I'm sorry, x sub 10, this is x sub 11, this is x sub 12, and so on and so forth, right? So when my user says, I want to put something in x sub 12, well, where is x sub 12? This corresponds to x sub 10, this corresponds to x sub 11, and this corresponds, this down here corresponds to x sub 12. So I have to have some way of translating the user's index, which is his logical view of this object, into the physical view, which really is some pointer, internal pointer p, to an array on the heap. And the easiest way to do that is, let's take a look what happens x sub, let's say, take the simplest case, x sub 10. X sub 10 goes to p sub 0, right? So x sub 10 goes to p sub 0. Where does x sub 10 goes to p sub 0? Where does x sub 11 go to? X sub 11 goes 1 over, that goes to p sub 1. And so on and so forth. So what you see is, in order to get from the index here, right, from the index in the x to the index in the p, right, in the index to the p, I simply have to subtract the lower bound that you give me, right? What's my lower bound? My lower bound is 10. So if you say x sub 10, so if I take 10, if I take, and your I is 10, here's your I, right? If I say p sub what, I take I that you tell me and I subtract the lower limit, in this case 10, that will be the right way to do this. All right? I hope that makes sense, right? So if you say give me x sub 12, well, what's x sub 12? This is 10, 11, 12. This is 0, 1, 2, right? So if I say, if I take 12 and I subtract the lower bound, which is, in this case, it's going to be 10, that's so that's going to give me a 2, and that will take me to p sub 2, right? That's the way it really works. So that's why, forget this for a second, we'll check this out, but if you say, give me x sub I, I'm going to take the I that you give me, let's say 12, I'm going to subtract low, in this case low is 10, 12 minus 10 is going to give me 2, and so I'm going to go to p sub 2. Okay, so that is how I make this thing an array, right? I map the index in your object, right, in your Safearray object x, into the real index that's being used internally, where the array p lives on the heap. Now, how do I make it safe? Well, that's the easy part. To make it safe, all I have to do is, when you give me a value of I, right, you're going to say, x sub I have to check to make sure that I lies within the bounds, right? I cannot be less than this and can't be greater than this. So that's what happens over here. I have low and high. So if you give me This part says like this. This part says that if the I you give me is less than low, or the I you give me is greater than high, I'm going to print a message that says the index I, print out what I is out of the range, and then I'm going to exit 1, which terminates the program. Okay, and finally, in terms of this operation, why am I returning a reference, right? I'm returning p sub, why don't I simply return an integer? Well, of course I can't return an integer because I want to be able to store in this, right? I want to say something like, x sub 11 gets a 25. That's what I say. So this thing has to give me the name of something that I can store into. If I just return the value that's at x sub 11, in other words, whatever number is stored in here, that's not going to help. You can't store a number into another. I have to give you the name of something. And remember, a reference is really the same as a name, right? So that's why I have to return a reference. So when I say I'm going to return p sub 11, I'm not returning the value p sub 11. I'm returning a name of p sub 11, a reference. And of course, if I return a reference, I can store into that location, right? So whenever you want to store into the location, you have to return a reference. And that's the whole story. That's the way it works. So how did we make it an array? We overloaded the bracket. Right? How did I make it safe? By having a test over here that just checks to see that you're in the bounds that you described. And finally, why did we have to make it that returns a reference? Because when it returns p sub I, that p sub I, I'm not interested in what's in p sub I. I'm returning a reference to the place over here so that I can actually store into it. Right. So, for example, just forget safe arrays for a second. If I have an array A, right, I have an array A size 10. Right. When I say A sub 3 gets 100, what happens is when I say A sub 3, I'm storing into it. Right. That's what we call an L value. It gives me the name of a place to store into. Right. Likewise, have to return the name of a place, which is going to be a reference. Okay. If that does not make too much sense, please listen to it again. Listen to it again because it has to be absolutely clear. This is foundational. And finally, to end the whole thing, we want to be able to read and write our safe arrays. So I want to be able to take a whole safe array and I want to say cout my safe array X, and it should just print out the whole array. And there's nothing new over here, right? We saw this when we spoke about rats. First of all, it can't be a member function for the same reason that rats couldn't be a member function, right? Because remember how a member function has to look. You have to have a class object over here and a dot and whatever function, whatever parameters. So my function has to work on an object of the class. In this case, the class is a safe array. But a cout is not a safe array, right? So this would actually have to translate into cout dot operator left shift of X, and that doesn't work, right? Because if this were a member function of the class, this must be a safe array. So it can't do that. The same exact reason that we saw when we look at rats. So we fix it up by making it a 2-parameter function by overloading the brackets, but it can't be a class member function, but it can be a friend. Remember what a friend was, right? What a friend was, it has all the access privileges that a member function has. And we did this extensively when we talked about the rat class. If you don't remember it, please go review the rat class. So how do we do this? So we have this operator left shift, and we pass in a safe array as the right hand. And we saw the last time that customarily you would write it more as I'm passing in a const safe array reference. Like that. But normally, why would you do it that way? Because when you're writing, first of all, you're not expecting to change the thing that you write. Right? When I print out the value in my safe array, I don't expect the implementer of my function to be able to change anything, so I declare as a constant. And why is a reference? Well, why not? Because why should I pass in a whole safe array object by value? Remember what's going to happen if I pass it in by value. If it's a large safe array, I'm going to have to make a whole local copy within the function. That's ridiculous. Imagine my safe array has 1 million elements. Why do that? Especially, the only reason I would pass by reference is by value is I want to make sure nothing changes. right? Or if I want to change it, I pass by reference. But the whole idea here is I don't want anything to change, right? So I accomplish that by saying it's a constant, and then I pass in the s by reference. If I didn't have it as a constant and I passed it by reference, of course, he could change it, right? So by making it a const reference, it's a very well-known trick. You make it a const reference, so you make it a reference because you save having to copy the value locally. By making it a const, it can't be changed in the function. Anyway, so that would be the normal way to do this. And why do I have an O-stream reference, right? Because the whole idea, in this case, the O-stream would be cout, right? I'm writing to the cout object. The whole idea is that I'm writing to the cout object. When I put something in the cout object, cout is called a stream object, I'm changing the internals, right? There's an array in there called a buffer. The buffer gets changed by the value in S. So of course it has to be a reference because I want to change it. Okay, so that's in terms of the header of this function. And it's the same as I did before. What this is going to do is remember what's being passed in over here. S is being passed in. S is my safe array. In the safe array, I've already defined the bracket operator. Since S is coming in by since S is the parameter, it's not the left-hand side, right? And it's not because this is not a member function. S is the parameter, but this is a friend function, so I can say from the parameter S, I can say S dot P sub I, right? Because P is pointing to the array that lives in the heap, but I have to modify that by saying the parameter name, and I can do that. I can use the dot over here, and I can use the P in here because it is a friend. So all I'm doing is I'm going from P sub 0. Remember, inside the array on the heap, it's P goes 0, 1, 2, 3, and so on. Even though on the outside X could be going, say, from 10 to 20, but internally it's going from 0 to whatever. And so therefore I go from 0 to size minus 1, and I print out P sub I, S dot P sub I, and that's the story, right? And of course, at the end, as we saw before, in order to facilitate chaining, I have to return whatever stream came in, right? And it's going to be returned as a O-stream reference because the whole idea of chaining is I want to be able to write to it. So now I can say cout, some variable I, and then say cout X, where X is a safe array, and then I can say cout high, and so on down the line. Okay, and we saw how this thing works. I'm going like this, and I'm going to print I, but what's going to come out is the cout, and because cout is an object that's passed by reference, I can now do this, and X will be input into the cout object, right? Because it's something I can write to, and then cout is going to come in again, and I can write high into this, and this is exactly what we spoke about when we spoke about the rats. Okay, with this, we have finished the Safearray class, and we can use a Safearray class once we have it. So here we're writing our own sort, and you know how sort works. It's a bubble sort, and if you look at that sort over here, what's going to happen is I'm going into the Safearray. Here's my Safearray K, passed by reference, so I can move it around. This is the size, and I can do the sort because I can access the elements with the brackets.